Hey guys, this is Sean with Alexander Tutoring, and today's lesson is on graphing rational expressions, functions. Because I know a bunch of you are working on that right now. Our lovely tutor team let me know that that's what a bunch of you Algebra 2 peeps are working on. And I recognize that these are pretty intimidating and long. So I want to make this easier for you. The good news is there's a set of steps you can follow every single time that always works. And I've written these steps out for you here. And each of the individual steps isn't that hard. So if you can just follow the steps, it's a little long, but you can do it. Okay, so let's go through the steps and then we'll do them on this example I have written down here. Step one, factor everything as much as humanly possible on the top and the bottom. Step two, find the x-intercepts. So if you're on the x-axis, you know for a fact that y is equal to 0. So we'll set y equal to 0, solve for x. Then we'll do the y-intercepts. If you're on the y-axis, you know for a fact that x is equal to 0. So we'll set x equal to 0 and find the y-intercepts, put those on the graph. Or we'll find the vertical asymptotes, which occur whenever you're dividing by 0. So we'll basically look at what values make the denominator 0 and put a vertical imaginary line there that the graph can basically get closer and closer to, but never quite touch. Then we'll do horizontal asymptotes. Same idea, except horizontal. Now, there's three cases we have to look at for the horizontal asymptotes that we'll go over, and it has to do with the degree of the top and the bottom. So the degree is the biggest power you see. In this case, the degree, or at least seemingly from here, is 2, because there's an x squared is the highest power on top, and an x squared is the highest power on the top. So we have to look at the case when the degree on top is bigger than the degree on the bottom. We have to look at the case when they're equal, as in this case, because it's 2 on the top and the bottom. And we have to look at the case when the degree on the top is bigger than the degree on the bottom. Um, so we'll do that on step 5. Finally, we plot a couple extra points in various regions of the graph just so we can connect the dots and get our final graph. Okay, so here we go. Let's factor as much as humanly possible. So the top is a basic quadratic. So we want to think of two numbers that add to get the middle term, which is 1 in this case, and multiply to get the c term, which is -6. So we can see that 3 and -2 do the trick because because 3 minus 2 is 1, and 3 times -2 is -6. Okay, and then we can see on the bottom that there is a -4 common to all three terms. So we're going to pull that out, plus 4x plus 3. And then we have another quadratic in the parentheses there, which can be factored just like we did the top. Four. Okay, and now we have a middle term of 4 and a c term of 3. So what adds to 4 and multiplies to 3? And that's pretty easy. We get 3 and 1 to do the trick. If you need any help with factoring, I've sent a couple of videos on that already. Be sure to check those out. Now, okay, we factored everything as much as humanly possible, except one little thing I want you to notice is that the x plus 3 on the top and bottom factor cancels. So really quick, before we cancel that, I want you to see what happens, because what if x equals -3? Well, then you have 0 over 0, and that's a big no-no in math. So let's go on to step 2 and find the x-intercepts, and I'll show you what happens. Now, you get an x-intercept when y is equal to 0. And the cool thing about factoring is you can see really quickly which values of x give you a 0 for y, because if you have a 0 in the numerator, um, it's definitely going to be 0 unless you have a 0 on the bottom, right? So just to prove a point, let's see what happens when we put 2 in. We get 2 plus 3, 2 minus 2. There's your 0 in the numerator. And then we get -4, 2 plus 3, 2 plus 1 equals, we have a big fat 0 up top, right? Because of the 2 minus 2. And then we don't really even care what we have in the bottom as long as it's not 0. So that's what 3, 5, 15, 60. Who cares? It's 0, right? So x equals 2 is an x-intercept. And we could have seen that right away just from the looking at this guy right here. Okay, so let's go ahead and put that on there. So x2 is an x, change color. We have an x-intercept right at x equals 2. Let's stick that on the graph. All right, now what about this weird -3 case that I wanted you to look at? So it would looks like -3 should work too, right? Because of this guy. But let's just see what happens when we put, so we want y to equal 0 because we're looking for x-intercepts. We would get -3 plus 3, there's your 0. -3, let's see, -3 plus 3, there's another 0. And you can see that we end up with a 0 over 0. And that is a big no-no. Let's just finish this up real quick. So we would basically get 0 on the top times -5 over, we get -4 times 0 times -2. So what this looks like, we have 0 over 0, which is a big no-no, and what's left over is this -5/8. And what that tells me is that we have a hole, they call it, which is basically a spot that just doesn't exist in the graph at x equals -3 and y equals -5/8. So let's put that on. That's going to look something like that. That's a hole. Let's leave that for later. Okay, and that's it for the x-intercepts. For the y-intercepts, we simply set x equal to 0, so that's quite a bit easier. All we do is put 0 in for all the x's to get 0 plus 3 and 0 minus 2 over, oh, by the way, we can cancel things out now. I should have done that already. 0 plus, okay, so y equals, we get -5 up top. Let's see, that's 3, 1. Oh, sorry, -6 up top over -12. We have a y-intercept at 1/2. Let's stick that guy in there. Okay, so you can kind of see we're getting some information on the graph now. Very cool. By the way, one thing I could have done earlier, I just realized, is um, going back to our original function. Remember I said the 3's cancel? Now that we've put that hole in, we can cancel those guys, and I'll take this over to the next page. We get something much easier to look at. We get y equals, that's what's left after the x minus 3 is canceled out, and you can see that that is a bit nicer to look at. Okay, we've done our x and y intercepts. What's next is vertical asymptotes. Vertical asymptotes occur when you divide by 0 because you can't divide by 0, so the function can't touch that point. And the beauty of factoring is we can see right away that x equals -1 is where we divide by 0. So to find a vertical asymptote, you find what values of x make the denominator 0. And we can see right away that x equals -1 does the trick. Okay, so let's go put that in over here. I'll get a nice color. And what did it say? -1. We have a vertical asymptotes. We do a dash line like that. Okay, progress. Next, we have to do the uh, horizontal asymptote. So remember, there's 3 cases to look at for that. So I'm going to call the numerator, sorry, the degree of the numerator, which is the highest power you see in the numerator. I'm going to call that n. And I'm going to call the degree of the denominator, or the highest degree you see in the denominator, d, just to make things easier. So case 1 is d is greater than n. For example, if we had something like x squared plus 2x minus 1 over, okay, in this case, the highest degree of the denominator is 3, right? Which is bigger than the highest degree of the numerator, 2. And so to understand horizontal asymptotes, we have to think about what happens when x gets really, really, really big. So if x was like a billion, what we can say, looking at my example here, is that the highest uh, degree terms, the x squared and the x cubed, are going to be so much bigger than the other terms. The other terms are basically negligible. We can almost ignore them, right? If x was a billion, because a billion squared and a billion cubed is so much larger. However, a billion cubed is way bigger than a billion squared. So this thing, as x gets really, really large, is going to get closer and closer to zero because what you're dividing by a really, really, really big number. So in the case when the highest power in the denominator is bigger, you're going to get a horizontal asymptote right at y equals zero because right on the axis here. Because as x gets really, really, really big, you get closer and closer. Y gets closer and closer to zero. So you might have something like this. Okay. Case two, which is our case, uh, the degree of the denominator equals the degree of the numerator, which is our case, right? Because now our degrees, once we've simplified, are one on the top and the bottom because the highest power of x is one on the top and the highest power of x is one on the bottom. So they're equal. What we have to do when they're equal, let me show you what happens. So this is our function. I'm gonna, just to make it easier to look at, I'm going to expand out the denominator. Okay, so again, with horizontal asymptotes, we're asking what happens when x is really, really big? What happens to y? So if x was like a billion, this -2 and -4 would be basically irrelevant. And what would we be left with? Like a billion over -4 billion, right? And the idea here is that the x's basically cancel in that case, and what's left behind is the coefficients, right? So in the case where the degree of the numerator is the same as the highest degree of the denominator, basically you ignore all the other terms except the leading terms, and then the x's basically cancel, and you're just left with the coefficients, which in this case is 1 over -4 or -1/4. So this is our um, horizontal asymptote. I'm going to go stick that in really quick while I'm still thinking of it. Okay, so we get a horizontal asymptote um, at -1/4. So like there, okay? We're making serious progress. Find the vertical, horizontal asymptotes. Before we move on to the last step, I just want to give you the third case, which is the hardest case, and that is if um, d is less than n, that is the degree of the numerator is larger than the degree of the denominator. This actually splits off into two cases. Case one, if the degree of the numerator is exactly one bigger than the denominator, for example, in this case, the degree of the numerator is bigger than the degree of the denominator by exactly one. It's one bigger. What you have to do in that case is do polynomial long division. You divide the denominator into the numerator. I did a video on that too, you can check out. And then you're going to get the equation of a line, and that will become your slant asymptote. I'll do that for a different problem, but that's what you do when the degree of the numerator is exactly one bigger than the degree of the denominator. Case two is it is more than one bigger. Okay, so like if you had x cubed plus 2x minus 1 over x minus 1, now it's two bigger. So if it's anything more than one bigger in the numerator, there just isn't one. Okay, because what happens when x gets really, really, really big? Well, the numerator is just going to explode to infinity, right? Nothing's going to cancel it out. So that case isn't too hard. Okay, so we're almost there, guys. I know this is a slog, but I just really wanted to go over all the possible cases you might see. Last step 6 is we're going to plot a couple points just to help us connect the dots. We already have a pretty good idea. Sometimes you don't even need to do that because I can already tell you what's happening in the upper right quadrant. We know that it has to be an asymptote here, and we know that it has to go through these points, and then we know there's an asymptote here. So it's got to look something like that. And then over on the left side of that vertical asymptote, well, I'm not really sure what's going on. This is where plotting some points can be helpful. So I'm just going to do it right up top here so you can see it. So what we are left with is x minus. So remember, when in doubt or you're not sure, always just plug in some random x values. You can always do that. It always works, right? All right, so let's say what's going on at x equals -2, for example. Let's just because I want to know what's going on kind of over in this left region. Well, then we get -2 minus 2 over, I'm running out of space, but that's -4 over -2 plus 1 is -1. Okay, so we know that there is a point at x equals -2, y equals -1. And now I'm getting an idea. That's really all we needed, right? Because I can now connect the dots. So we know we have an asymptote here. We have to asymptote out with. We know we have to go through but not touch this hole we came up with, right? And we know we have an asymptote here. So it's got to do something like that. And that is enough information to complete your graph. Congratulations, you have made it. So always remember though, if you're ever lost in these, you can always plot in a few extra points, plug in x equals -3. That's a great way to check your answer on an exam, just to make sure you're correct. Plug in x equals -3, -4, +3, whatever you want, just to make sure it looks good. All right, that was a long one. Thanks so much for watching, guys, and I will see you. I'll make another one of these for you so you can see a different example for the next video. All right, good luck. Have a great one.